What if AI could not only predict how proteins interact, but also design new ones to combat diseases like COVID-19 or cancer? In this video, we're exploring two groundbreaking AI models, AlphaProteo and Orb, that are revolutionizing everything from drug discovery to materials science. Before we dive in, take a moment to subscribe to stay updated on the latest AI trends. You probably know that proteins are essential for various functions in our bodies. They help cells grow, keep the immune system running, and are crucial for nearly every biological process. However, proteins don't work alone. They interact with other proteins, much like how a key fits into a lock. These interactions are essential for the critical functions inside our cells. Thanks to AI models like AlphaFold, we now have a solid grasp of how proteins interact. AlphaFold predicts these interactions, which has been a major advancement in science. But here's the catch. While AlphaFold is great at predicting interactions, it doesn't create new proteins to manipulate or influence these interactions. That's where the magic of AlphaProteo comes in. Enter AlphaProteo, developed by Google DeepMind. This AI doesn't just predict interactions, it designs entirely new proteins that can bind to specific target molecules. Why is this important? These new proteins, called binders, can accelerate research in fields like drug discovery, understanding diseases, and developing pest-resistant crops. Let's break it down. Creating a protein that binds to a target, like a viral protein from COVID-19, is difficult. Traditional methods are slow, involving numerous cycles of testing and optimization. However, AlphaProteo changes that by taking a major shortcut. Trained on massive protein datasets, including over 100 million predicted structures from AlphaFold, this AI can now design binders that perfectly fit target proteins. It's like handing over a blueprint for a lock and having the AI design the perfect key. AlphaProteo has already demonstrated success by creating binders for 7 different target proteins. When tested in labs, these AI-designed binders worked exceptionally well, binding 300 to 300 times more effectively than the best existing methods. For example, it created a binder for VEGF-A, a protein related to cancer and diabetes complications, marking a significant milestone in AI-designed proteins. And it's not just a one-off success. For the viral protein BHRF1, AlphaProteo's binders worked in 88% of cases, with an average binding strength 10 times stronger than the best existing designs. The system even created successful binders for the SARS-CoV-2 spike protein, which is responsible for helping the virus enter human cells. These binders were tested by top research groups, including the Francis Crick Institute, and they confirmed that AlphaProteo's designs could block the virus and some of its variants from infecting cells. However, the technology isn't flawless. AlphaProteo couldn't design a binder for TNF-A, a protein associated with autoimmune diseases like rheumatoid arthritis. But that's to be expected, as TNF-A is notoriously challenging. The team specifically chose it to test the system's limits. Even so, AlphaProteo has already overcome one of the toughest challenges in protein design. The team behind AlphaProteo is now collaborating with scientists worldwide to further improve the system. They're also thinking carefully about biosecurity, ensuring the technology is used for positive outcomes like treatments and environmental cleanup, rather than for harmful purposes. They've teamed up with organizations like the Nuclear Threat Initiative to set best practices for using this powerful technology responsibly. Looking ahead, AlphaProteo's team is exploring drug design applications through partnerships with companies like Isomorphic Labs. They are continuously refining the algorithms to make the system even more powerful and versatile. Now let's talk about another exciting AI breakthrough. Orb, a revolutionary AI model in materials science. Orb is designed for simulating advanced materials, and it's fast, blazing fast. It's also open source, leaving even big names like Google and Microsoft in the dust. If you're into AI, energy, or cutting-edge tech, you'll love this. Scientists working on materials like batteries or solar panels need to understand how atoms and molecules interact on an atomic level to design more efficient materials. Traditional simulation methods are slow and expensive, often leading to oversimplified results. But Orb changes that. This AI model can simulate materials faster and more accurately than anything else available right now. Orb was developed by a company called Orbital and is based on a larger AI model called Linus. Orb is 5 times faster than the best alternatives for large-scale simulations, and it's outperforming models from Google and Microsoft in both accuracy and speed. And the best part? It's open source, free for non-commercial use, allowing startups and researchers to access it for developing new materials. This is crucial because as we shift toward renewable energy, the materials we use need to improve. Whether it's batteries for electric vehicles or semiconductors for technology, faster simulations will accelerate the development of better, more efficient materials. Orb is a key tool in that process. Orb's development ties back to Linus, which the Orbital team has been refining for a while. They've fine-tuned it specifically for advanced material simulations, and it's paying off. Despite being a small, tight-knit group, Orbital is competing with AI giants like Google and Microsoft, proving that even smaller startups can lead the way in groundbreaking technology. So there you have it, Orb, the fastest and most accurate AI model for simulating advanced materials, and it's available for free for non-commercial purposes. I can't wait to see how this technology shapes the future. Let me know your thoughts in the comments, and don't forget to subscribe for more deep dives into AI and tech. Thanks for watching, and I'll see you in the next one.